Hello all, I am Dr. Sujatha, Assistant Professor, Department of Mathematics, RVCE. Today in this session, we shall discuss few properties of Laplace transform. We all know that Laplace transform is a method of transforming a time variable function into a complex variable function. In recent years, the theory of Laplace transform has been an essential part of solving many problems arising in engineering. The basics, the definition, and the Laplace transform of standard functions we all have already studied. We all know that. Today in this session we will discuss few properties of Laplace transform. So today I shall discuss the linearity property and the scaling property of Laplace transform. So to begin with, the first one, linearity property. So when we had discussed the Laplace transform of standard functions, we had come across with a function called sine hyperbolic at and cos hyperbolic at. So when we found Laplace transform of those two particular functions, what we did was we were able to express hyperbolic functions in terms of exponential functions, and later we wrote down the Laplace transform of both the functions as sum of two exponential functions or the difference of two exponential functions. So that what we had presented there was nothing but the linearity property of the Laplace transform. So to state that if we have two functions f of t and g of t, and we know that the Laplace transform of these two particular functions exist, then the sum of these two functions or the difference of these two functions multiplied with some constants a and b, that is L of a f of t plus b g of t, can be written as a into L of f of t plus b into L of g of t. So if it has a very simple proof here. What is that is, we begin with the basic definition of Laplace transform. We all know that Laplace transform of f of t is integral from 0 to infinity e to the power minus st f of t dt. So now what I will do is, I will replace the function f of t by a f of t plus b g of t. This a and b are some constant numbers which can take the value 1 in a particular case. So now I can write that as a into integral from 0 to infinity e power minus st f of t dt plus b into integral from 0 to infinity e power minus st f of t dt. So which is nothing but a L of f of t plus b L of g of t. So if you have sum of two functions, then finding the Laplace transform of the individual functions with the sum is what is the linearity property. So to demonstrate linearity property, let me take up an example, sin t into cos 2t. We know that sin a cos b is half times of sin a plus b plus sin a minus b. So sin t into cos 2t is written as half sin 3t plus sin minus t. And we know that sin of minus theta is minus sin theta. Therefore, sin t into cos 2t is equal to half sin 3t minus sin t. I will take Laplace transform on both the sides. So L of sin t cos 2t on the left hand side will be equal to half L of sin 3t minus sin t. So on the right hand side, I have a term L of sin 3t minus sin t. So I shall write down that as half into L of sin 3t minus L of sin t. So I have applied the property which we had discussed, which is nothing but the linearity property. So which I can now write it as half Laplace transform sin at, which we know it is a divided by s square plus a square. So Laplace transform sin 3t will be 3 divided by s square plus 9. minus, similarly Laplace transform sin t is 1 divided by s square plus 1. Therefore, Laplace transform sin t into cos 2t will be equal to half 3 divided by s square plus 9 minus 1 divided by s square plus 9. So this particular example exhibits the property of Laplace transform, which is nothing but the linearity property. Now let us discuss the scaling property. Let me multiply by a factor a in the time domain. It so happens that in the frequency domain, you will see that there is an inverse scaling happening. So the scaling property is being stated in this way. If a is a positive constant, then Laplace transform of f of at is equal to 1 by a f of s by a. So scaling in time introduces an inverse scaling in s. So that depends on the sign of a there. For example, let us take the function sin t. We all know the Laplace transform of sin t is 1 divided by s square plus 1. So f of t was sin t. The Laplace of f of t is 1 by s square plus 1. So now, what is Laplace transform of f of 2t? I have scaled by a factor 2 in my time domain. What happens in the frequency domain? So by the application of the scaling property, a is 2 here. So in the frequency domain, it has been scaled by 1 by a, that is 1 by 2. So L of f of 2t will be 1 by 2 f of s by a. So f of s is nothing but 1 divided by s square plus 1. So now half times of 1 divided by s by 2 whole square plus 1, which on simplification we write it as 1 by s square plus 4. So this particular example demonstrates the scaling property. Similarly, let me take up one other example. We all know the Laplace transform of sin t by t is cot inverse s. So now let us find the Laplace transform of sin at divided by t. So here, to apply the scaling property, I have to scale in the time domain by the term a. In the denominator, I found that there is only t. So what I will do, I will multiply and divide by a, the term a. So a into, I will get the term L of sin at divided by at. And that is nothing but L a into L of f of at. So if you scale, you get a into 1 by a f of s by a, which is nothing but the scaling property. So with the application of that, we observe that Laplace transform sin at divided by t will be cot inverse s by a.